Right.
Will stop working right, so like even the recording thing. Let's see, so this thing, and then I just want to go through that homework 11, right? This guy, there's a couple points here. Sorry, I'm not super functional today. This guy, then I need to get this guy over here, the supplemental sporting info. And then I gotta hide this thing. And then I need yes, I wanted to cover membranes, and anyway, it's gonna take more than one day. Like we got today and then probably one another day or something. But there's a homework 12 is on membranes. Bailey wine. Where's the supplemental? Oh, I already opened supplemental for Yavit. Then I need the supporting info for Schweitzer. All right. So blah, blah, blah. I went through this last time. The relaxation time for the matrix, and then there's the relaxation time of the beads in between, and those add up into his this function. So this is a matrix part, and then there's this Arrhenius function. And then it's like, what is the Arrhenius function? Is it appropriate here? I think everyone kind of did that. This is not, so someone said it's like a thermally equilibrated. So this is a kinetic model, right? So you got to think like kinetics and thermodynamics kind of like not together, even though it has energy in it. So it's not a thermally equilibrated because you have something moving, I mean, it could be steady state. But there's a difference between steady state and equilibrated. So it's thermally activated. It's the magic word, right? So because you have this barrier energy. So I guess Arrhenius was chemistry, but basically like the Irene rate law just covers any kind of rate process. It's the same function. So I think generally it's just a thermally activated process. So the question is the motion of the beads between the two of the polymer beads between two nanoparticles, is that motion thermally activated? And I mean, you could probably argue it either way, but yes is probably the simplest answer. So everyone answered yes. So when you see someone uses Arrhenius, then you should ask, is it appropriate there? That's kind of like, and then know what the basis of it is. That's the idea of that. Then let's see. Nanoparticle correlation function, separation distance, blah, 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 Rm and all that business. So that's his, that's this business, like this plot, right? So anyway, I went through it last time. Let me hide this thing. Anyway, so this plot, the last plot's probably the best place to start on this thing, like, because it shows the energy. So this is the PMF, the mean field, the potential of mean force. So the energy of a particle is a function of position, right? So like the separation distance of two particles. So you can see there's like wells in it. So there's places where the particles can land. There's a bigger barrier when it gets closer. So it's harder for it to get close than it is to go to the second well. So it's easier to fill up the second well than the first well, because the first well is at a higher energy. So when it's dilute, it's like that. And then the weird thing is that as you increase the concentration, those barriers get smaller. So I guess that's because the particles are squeezing in somehow, right? So that lowers the potential. But somehow they push each other, and then the wells get smaller, the barriers get smaller. So that means that it can populate when it gets to higher concentration, the higher energy, higher barrier well thing. So anyway, since there are none at that close one for the dilute, I mean, he takes that as like the barrier. So he takes both of those as a number. So Rm is how many of these beads are in the closest and the second closest. And then he shows it as a bilayer. So I guess that's true because the position of this thing remains in the same place. And that's because of the shape of these energy things. And then this is the delta W times the integral of this up to Rm gives the MB, the number of beads in the bilayer. So that number of beads times this barrier that they had to go through. So they had to get over that to get into that region. So that's like the energy for this delta E. That's going to be the energy that's in this equation, right? To get the relaxation time of the beads of the whole system. But you can measure with the dynamic X-ray scattering. So you do X-ray scattering, you find out where the bead peak is. And then you look at that as a function of time, you find out that the time correlation of that. So you take time here, time there, and then kind of multiply the two intensities with the same delta T, and they do that for every possible bead situation. So at that Q value, then you can plot that versus time, and it'll be a decay. Like when it's a 0 time difference, then it's always 100%. It's like the same number squared. And then when they go apart, that decays because the correlation between them drops. And that correlation is related to the diffusion coefficient of the particles or of the beads, whatever it is you're looking at. But here you're looking at the particles because it's X-ray scattering. If it was neutron and you deuterated, then you could look at the polymer moving. You look at deuterated polymer moving, right? So you get that relaxation time, then you can get the tau from that. That's the tau. That's like this tau, right? So then once you have that tau, then you can get the delta E, and then you can backtrack and get everything. That's one of the questions, like how do they do that? So they do like time temperature superposition of that to get the range of the tau or something, get the activation, and then you can get delta E from that. Anyway, that's the deal. This is an integral of how many particles are in each of this. This is kind of like the integral of the correlation function. So that's a cumulative how many. And then it's like how many, and there's some in the first, and there's some in the second, and there's all the rest of them. I don't know why this doesn't go to like 1 or something, but it's not normalized, I guess. So anyway, so that's kind of the question. People variably got that more or less, like. So that's delta W, and then show interesting. This is about the other plot. This is about not this plot, but this plot, and it. So I think everybody got this. Like, why does the number increase with loading? That's got to do with this energy plot. Really, everything has to do with this plot in the end. Like how you can get more because the barrier is lower as you increase the particles. The barrier is lower because they crowd in. So that's why it increases with concentration. And then if you, this particle polymer nanoparticle interaction energy, right? As you change that, then that shape of that changes, or the steepness of it changes. And then if you anyway, so if you let's see, what is this thing then? Ln of the correlation function, total versus concentration. This comes from a function for that, like this exponential function for the correlation function. Like this thing's exponential, so the log of it. That's just demonstrating that that function works, I guess. Which is, I think this is an empirical function. I'm not sure. No, it's just an Arrhenius function. Yes, beta AP. So that's just showing it's an Arrhenius behavior or something. That inset. This inset. It makes sense that you have to subtract off the EPN if you figure out where delta W came from. Let's see, delta W, anyway, delta W somehow has EPN in it. So if you subtract the EPN off, then they become the same number. So this is self-evident. And this thing, the lambda to me is still kind of mysterious, but it has something to do with, so he never, did anybody figure out this thing? Like he never said, he defines lambda in terms of the ratio between EPN and EPN0, right? But what is EPN0? I never could really figure that out. Like he doesn't say what it is, right? So, but apparently it's some number, and then it makes it, anyway, he shows the lambda versus EPN or something here, right? There's a plot. So anyway, lambda is something that has to do with the interaction energy, but it's pretty hard to tell what it is. He never explains what it is as far as I can see. I don't think anybody explained what it was. So lambda is kind of a weird thing. So anyway, the question is like kind of hypothesize what it could be, you know, because he doesn't say what it is. So anyway, and then then it's like delta E, how do you measure it experimentally? So they do that dynamic X-ray scattering measurement. They do a time temperature superposition to activation, and they do a plot of that versus Q, yeah, or something, size. Right.
Q, 1 over Q.
Yeah, 1 over Q is like size, right? So, and then the lambda is a mystery. I guess people answered it pretty good, better than I could probably. The same, let's see. Then there's this discrepancy, but the fit is pretty good. And the Yevet thing, they show that fit, like it matches pretty well, like the red and the dotted red and the blue, they're right on, you know. I mean, I don't think there's much discrepancy. If I did that measurement and that simulation, I'd be pretty happy because the measurement is taking a chunk of gunk and sticking it in the beam, you know? And the experiment, the simulation is like these model. So I mean, if you got that kind of agreement, I think that would be pretty sweet. But granted, like they shift the peak around by this E thing, I think. So the E is kind of a floating parameter, and they kind of determine the E from the experiment. EPN, you know, eta PN. So there is a little bit of fudging it, but basically, I mean, as far as the presentation, it looks pretty clean to me. And polydispersity, I mean, of the polymer and of the particles, surface contamination, I mean, anything could cause it to broaden out. The peaks are broadened out, that's it, right? So I'd say that's almost like perfect. Like I would be really happy with that. So he talks a lot about the discrepancy, but I'm not sure why. Anyway, so that was kind of like to look at that paper, you know. Any questions on that thing, or hopefully it's okay. So anyway, I wanted to do membranes. I'm kind of still in the process of putting together some stuff on it, but I thought I'd go through today some. And then there's a homework on Friday that's on membranes. It's like, all right, so there's a Nature paper. And I asked someone that works in membranes, like, what's a good recent paper on membranes that has something to do with physics? They said, oh, this Nature paper by these British guys, it's the best thing, you know. And I'm like, so I said, okay. So anyway, I didn't really do any searching, I just used that. But that paper is it's about quasi-elastic neutron scattering and watching the water in a polyamide membrane. And in the way they analyze it, it gets pretty deep. So they look at the proton relaxation in the membrane, like to figure out how the transport's going to happen and what the mechanisms of transport are. And then they, anyway, there's the protons in the polyamide, so they have to subtract that out. So they do measurements to get that, and then they do measurements to get the bound water and unbound water kind of thing, like free water and then water that's stuck inside on the surface. Anyway, they can identify all that more or less. In the end, I'm pretty surprised that paper's in Nature, because Nature is supposed to be something that anybody could pick up and read. And this paper is definitely not something that anybody could pick up and read. And even the conclusion is hard to figure out what they even conclude. So it must be a political thing that they got that in Nature. But anyway, we got it for this week, for Friday. I'll talk about it on Friday.
About the Monday presentation.
Yeah.
Was there anything practical out of that? Because it was all simulation stuff. Like it was
Yeah.
So it wasn't like recording data for actual like any like molecules or anything like that, right?
Yeah.
So was there any like actual application for that? Because it seemed like
that would be a good thing to ask him, you know.
I didn't want to like I was going to ask him.
Oh no, you can't offend people, you know. Don't think like you're going to offend someone, you know, because everyone's thinking the same thing. Like, why are you bothering to do this?
Because there's like a lot of assumptions where he was like, yeah, like you set these two ends, and then like they like make a straight line when they relax. Like that makes sense in like theory, but like how to actually like apply that to something seems kind of impractical.
Well, I mean, all right. So the plateau modulus is important, right?
Yeah.
And like knowing where that comes from is important.
Right.
So he was able to calculate that number directly from this weird straightening out the chain thing.
Yeah.
So that means that I mean, the inference is that that's why that happens, you know.
Yeah.
So,
like, I was like, okay, cool, I guess that kind of makes sense if you have like a large molecule, like perhaps you could do it.
mhm,
And then he was like, at the end, he was like, yeah, but those would work for like larger proteins, but like, because like obviously they have like beta sheets and alpha things would be different.
yeah.
But like, okay, well, I don't even know when like that would kind of be applicable.
Oh, for synthetic polymers,
So just for like very large synthetic molecules, like very linear.
and as long as they're longer than the entanglement length, so that's not that long. That's like 10,000 grams per mole.
Sure.
So like most of the stuff you have is 100,000.
Gosh, okay.
So, I mean, you're not going to modify your extruder, but it's kind of like understanding how things are going.
Yeah.
So, I mean, I can see what you mean. Like it doesn't mean anything.
Yeah.
I mean, you're not going to get rich with that. It's not going to patent it or something.
Sure.
But there's something to be said about understanding how things work.
Yeah.
So that's the idea. Like the thing's complicated.
Yeah, kind of push the ball forward.
Yeah, I mean, it's a mess. And then I don't know. I mean, it's a mess. And then you want to try to pick out things that make sense,
Yeah.
So you try to, and the pieces of it aren't new. Like he's following exactly what people have said to do, It's just people haven't exactly done that. So I mean, he did it early with the single polymer, and then now it's a blend of polymers. And how does it change, So if you mix two, so say you can get the plateau modulus from the entanglement molecular weight, you can calculate it. But if you have two mixed polymers, then what is the entanglement molecular weight, And what are the features of the polymers that would give you the average entanglement molecular weight?
Yeah.
Right? Of
Yeah.
two of a binary mixture.
Yeah.
And first off, there aren't many binary mixtures. Okay, like there's only a few.
Right.
Like there's Norel, there's a couple that are commercial. Actually, there's two that are commercial. So the rest of them are just oddities, academic oddities, more or less.
Yeah, I found that like he was talking about like the sliding stuff and how that like was incorporated into the formula.
Mhm.
I was like, I went back home and did some like Wikipedia searches on it. I was like, that was very confusing for me as well. Like how that could be incorporated into some sort of formula, like that has to be
Sliding, like slip
random.
links or something, slip
Yeah.
entanglements when they slide.
That has to be random to a certain degree. Like if you have, I guess you could talk about like the flexibility or rigidity inside of it, but
I mean, that's addressing a problem. Like when you do the calculation, say you have a tube that's made up of entanglements, then you have a problem that you predict the viscosity would go to the power of molecular weight to the 3, and it's actually 3.4. So you have to do something to make it go higher.
Yeah.
So that's why they introduce these other things, like the entanglements have a time where they disappear. That's one thing. And one is that they slide.
Yeah.
So there's a few things like that where they talk about why it would be 3.4. And that's like it's a power, so it's not just 3 and 3.4, it's a molecular weight of 100,000 to the 3.4 versus to the 3. The difference is going to be huge.
wow.
It's going to be a factor of like 10 difference or something, So anyway, for the viscosity, so if your extruder is 10 times more viscosity, it blows up, So that is important to know like why, but there isn't really an answer, I don't think. Like there's many answers. So there isn't a definitive answer. That's the way I see it.
Right. Yeah.
So the slip thing, I mean, it's a rabbit hole, and anyway, people are interested and they can argue forever about it,
Yeah.
And there's not really going to be a concrete solution to that problem, I don't think.
It's probably like one of those things where it like sits for a long time and so when it's like a discovery and people are picked up again.
Possibly, or it might be one of those things that it'll never be solved, because it's too complex.
Yeah.
So, and it might not have one answer too, so it could be multiple answers.
Sure.
And I don't know, if people can argue about it, they'll argue about it, and they can, as long as they can kind of make a living arguing about it, they'll keep doing that.
Yeah.
So, but there's only a few people that would even care, I think. But
there's probably only a few people that can actually like discuss it.
Right. Yeah, he's one of them. He's one of them. Yeah.
Actually care,
Yeah, because he started talking about that later on, and it's like he could list like boom, 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 this model, that equation in that paper. It's like, okay. And I'm kind of like you, like, well, that's great, So, but anyway, with the binary mixture, it's interesting, I think, because it's like there's two features he looked at, like the size, right? And then the rigidity. I mean, the fact that rigid things have a higher entanglement than flexible things is interesting, I think.
Yeah.
So that's counterintuitive. Like if you have, I mean, say you have straight hair or curly hair. He's saying that the straight hair is going to get tangled easier than the curly hair, which we know isn't true, right? I don't think it's true. Is it true? I don't know. I only have straight hair, so I only have one perspective on it, but I think curly hair gets tangled easier.
Yeah, but you would just think that like the amount of like,
I mean, I guess that
the
tells you
amount of,
that,
like change that it's happening,
yeah,
it's not just as linear, and you would think that that would cause a lot of like interactions with the things around it.
yeah.
But
That's exactly what he's saying, and everyone's saying is that it is nothing to do with the kind of idea you have about when you pick up the cables and they're stuck
Right.
together.
yeah,
So there's something else going on, because if you spill the spaghetti on the floor, you can easily pick up a spaghetti, like uncooked spaghetti. Right, so basically, but that's supposed to have much higher entanglements than the cooked spaghetti. So, yeah, this is kind of weird. So when you get to the molecular scale, the interactions aren't the same as like the spaghetti and the whatever. There's something different about it. That's one thing. And then
maybe since it's like straighter, that makes it like.
I mean, that's one thing, but the other, that's interesting to me. But then the other thing is that if you have a mixture of rigid and flexible chains, that has nothing, the entanglement molecular weight of that isn't affected by that. It's only affected by how big a monomer is, or how big a Kuhn unit is. I think that's what he said, right?
Yeah.
So basically, that's really counterintuitive too, and it kind of brings up also the idea like, what is an entanglement? You know, so again, like it is kind of like often Never Never Land, but at some point it matters, I guess. You know, if you want to predict like what's going on, and you have this picture in your mind, this cartoon of these spaghetti things hooked together, and like that isn't the cartoon. So if your cartoon isn't right, you can predict some things, but eventually you're going to hit a wall, you know, where it doesn't work anymore. So it's good to know, like, if your cartoon, test the accuracy of your cartoon in the
That
mind.
would make sense more in like a laboratory scale where you're kind of like growing polymers, like very like minute scale.
Yeah.
It's like, and like when you actually make these polymers, a lot of them they just throw monomers into the tank and let them mix. And then you get something. I was like, okay, that doesn't really make sense in terms of his presentation, because there's so much random interaction that's happening there. Whereas like if you actually grow like a linear thing, like whatever it's like a carbon fiber or something like that, it kind of makes more sense.
Yeah, okay. Like they're growing and they're going to form like a network or something.
Because then that way you can actually calculate like it's very hard to know what that local interaction is going to be, right? Especially like it's going to be random completely. So it's very hard to actually know what that system is without the computer.
Yeah.
And that would be like the only application that I can actually see in the future. But
oh, well, no, I mean, I think the application is like just understanding how things work, you know?
Yeah.
So, and you can only do that easily on a computer simulation, because it's going to be really take you a long time to synthesize different Kuhn size polymers. Yeah, I mean, that mix, okay, that mix.
Yeah.
Because you can do different Kuhn size polymers, but that mix, that's a whole nother story.
Right.
So, and maybe it's impossible. So maybe you can only do it on a computer. And then, but then you can predict like how things are going to work. I mean, I think it's useful, you know. I just think it's also like the temperature dependence and adding a solvent to it and how that affects the rigidity and the Kuhn size, you know.
Yeah.
And then maybe that can impact like the entanglements, and then you get the extruder, you know, because the entanglement is going to be the extruder. There's no useful polymer that's not entangled. So all the properties you have that you want, toughness and fracture strength and whatever, all come from entanglements. So that's the entire game, is the entanglements.
Yeah.
And those are kinetic, they aren't thermodynamic. So you can kind of only do it with molecular dynamics or some kind of thing like that. So anyway, I don't know, that's my argument. But it isn't, you know, it isn't like you're going to get a patent on it, I don't think. Maybe you could. Like if you could get the size thing, you could figure out an application. Then you'd have to demonstrate. You can't, a computer program isn't going to work for a patent.
Yeah.
You're going to have to like demonstrate, bring to market, or whatever they call it, bring to practice. So somehow you'd have to make it and show that it actually works, you know. It's like to get a patent on it, it would have some intellectual property value.
I mean, if you could, that would be absolutely amazing.
Yeah. I mean, it seems like it doesn't have to actually you just have to show to the satisfaction of a patent examiner that you did it,
Yeah.
So you could kind of lie in a sense, as long as no one really picks up on it.
Yeah. That's good.
And in the end, if it's really of value, there'll be other systems that show up, so you already have it covered on one thing, and like, yeah, that becomes obvious then. So anyway, who knows? I think there's value in it. But it is kind of a game, it's just like a game. So he's doing his hobby for a living. That's the idea, like you got some hobby, play pickleball or something, like he can get a living from it. So I think he could play pickleball all day long, like it would be good, I guess, until you get sick of it and pick up something else. But the simulations are pretty flexible, so you can do different stuff. Weird thing is he's at a place that does processing, like they have all kinds of extrusion equipment and stuff. So it's kind of an odd place for a guy doing simulations.
Yeah.
But anyway, it's a nice place. It's like kind of northern. Japan's got an island on the top that's frozen, and then an island in the middle, the big island. And then the top of the big island, up in the mountains, it's all ski resorts and stuff. So but they have monkeys there in the snow. It's the only place in the world where they have monkeys in the snow. It's pretty weird. So I think it's a pretty cool place to be and like visit or something. That anyway, so yeah, that's pretty good. Thanks for bringing that up. You can email him too if you want. I mean, he's pretty open to like whatever. But you could have asked questions like that. I didn't really give any time for questions. I guess I was asking him some stuff, so that was probably my fault. Anyway, so yeah, all right. So the membrane stuff, let me show you a source on this thing. So I got there's a book here, membrane book. There's a book on membranes that's actually, all right. So I got this book by looking at he cites it in the Nature paper. So I thought that's a pretty good book. And it looks like it's a pretty good book, like membrane technology applications. And then I don't know, it goes through a lot of membrane stuff, but it goes through also ceramic and metal membranes. So there's different kinds of membranes. Anyway, so that book's there, and there's a review paper that I thought was pretty good that I found, not from this paper, membranes review. It's in some chemical reviews, non-equilibrium, blah, 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 process for formation of membranes. So that thing is pretty good too, I guess. It's good to get at least two perspectives on a subject, I guess, if you can do it. So that's kind of my sources so far in this Nature paper. And other than that, I know a little bit about membranes, so I'm definitely not the world expert in it. But it turns out, like the membrane field is a lot of phase behavior, because you're going to go through phase separation to create pores in a membrane. It's all Florey-Huggins stuff. And then it's Florey-Huggins and then some kind of kinetics like Fick's law and Darcy's law to kind of form these phases, right? So there is kind of a physicsy mathematical part to it. So you're making either small pores or large pores. So you have, and then more or less the large pore is going to be like filtration, and the small pore is going to be kind of molecular sorting, more or less. And then there's a lot of other features to it. You can say microfiltration, ultrafiltration. And then of those, you can say you have a porous membrane, means you're going to do like a phase separation and make holes in like nano holes basically in a plastic. And that's going to be used to separate. And then there's also surface functionality and electrical conductivity you can use to separate too. So there's variety, or you could have like a dense membrane where you worry about solubility. So that they both kind of end up, because the pores are so small, you're almost like looking at solubility even when you have holes, right? Because it's so small that things have to kind of get into the holes. And then the holes just become the free volume when you have a dense membrane, like the free volume in the polymers. You have a solid polymer that's got a high free volume, like a rigid polymers like this polymer is rigid because it's conjugated. So it's got like double bond, single bond, double bond. So that means that ends up being a planar rigid structure, right? So this kind of, and it's got a lot of times you're talking about water separation. So you want to have some kind of polar groups that allow it to kind of, so it's hydrophilic, because you're going to do like either osmosis or some kind of protein separation or something. Usually water is a solvent. So usually you have like cellulose acetate or cellulose nitrate, right, for the material for this thing. Because those cellulose with the hydroxyls, hydrogen bonds too much, so you can't process it. So you have to put nitrates on it or put acetate on it to make it go into solution. Then it'll go into things like NMP, like the universal solvent. And then you can phase separate it by putting it into water, basically. It's hydrophilic, but it's insoluble in water. So you put it into an organic solvent and then precipitate out with a non-solvent. And then you can get some kind of structure from that. Or you can make the solution and cool it down and separate. You can get a structure too. So there's various ways to get this porous membrane structure. Dense membranes kind of pick the polymer, more or less, whatever you want to do. Right? So these polysulfones are popular. So again, they have polarity, and then these have like super strength, right? So polysulfones, like they use for prison plates, so they can't break it to kill each other. So like, I don't know, you can buy polysulfone plates, but one use is in prisons. It looks kind of like glass, but you can't kill anybody with it. And then anyway, it's strong. It's really strong. That's the idea, and it's polar. So it's got then acrylonitriles, this thing also polar. Then vinylidene fluoride is like you can put in, that's Teflon basically. So you can kind of it's resistant to attack by acid and things. It's kind of more expensive, but it's also polar. So kind of you're looking for these strong polar materials, and sometimes you want to have crystallization, like polyvinylidene fluoride will crystallize. The cellulose will crystallize. So basically, if it crystallizes, it adds another feature. You can lock in the structure. So you go through, put it in solution, and then somewhere along the line of phase separating, it gets into a position, so it's a high enough concentration, it can crystallize and will lock in the structure there. So you can use that as a tool to kind of fix whatever structure you have. And you have like a strong nanoporous structure from the thing. So it's kind of one of the ideas of this. So there's a lot of applications, right? Like, and a lot of value added things like this. The guy I talked to is saying like polyolefin, so separating ethylene from ethane uses 2% of the world's energy because they do it by cryogenic distillation. So basically when you refine oil, when you drill oil, the gas that comes off has got methane in it and propane, and it's got ethylene and ethane. So you can cool that down and then you can get a liquid, but the ethylene and ethane are like really close boiling points. So the cryogenic distillation of those is really difficult to do. So basically the size of them is quite a bit different. So you can use a dense membrane to kind of separate those two. So basically there's an idea right now is like popular to try to use a like polypropylene membrane to separate those two gases, and that's, again, it's like 2% of the world's energy use. So it's like, there's a big gain to be had in that, because all the polyethylene is going to come from ethylene. And the ethane, I think they just burn or make into ethanol or something. Anyway, then biomolecule separations is a big deal, like proteins. And then some of for the dense membranes, this polysulfones, these have high free volume. This polybenzimidazoles is this guy. So basically polyimides of these. So these this is the largest. This is like, I forget what the units are, but this has a free volume like 17. This is like 38 or something. I'm not sure what the units are on that, but basically it's twice the free volume for this kind of aromatic polyimide thing. So So that's why people go to that to get more free volume. Then you can, the free volume, you can calculate what the pore size is and how the pore size, in other words, it's a molecular pore size to separate gases, right? So anyway, it's big business. There's a lot of money in it, and it's a little bit of a mystery. It's all processing. So it's ripe for small innovations that you could get IP from. You know, it's easy to get IP here. So anyway, then the problems are like, depending on how the thing works, you can have the membrane can separate at the surface. So whatever it is you're trying to remove can pile up at the surface, so foul, or it can like go into the pores and allow transport only of one of the two components that you're trying to separate, and then it can get stuck in the pores. So depending on how that separation is going on, you can either defoul it or not be able to defoul it. Like if it's stuck in the pores, it's stuck. But if it's on the surface, you could run it backwards and flush it out periodically, right? So anyway, so these kind of issues. And then if it's under high pressure, you can densify and crush the pores. That's another kind of lifetime issue with these things. So I thought like the best thing, this book has a chapter on how to make. So I thought that was kind of the most interesting part of this thing. So this is how you do it in a lab. This is called a doctor blade, and you put your solution of if you can just do evaporation to get structure formation, so you can make a polymer solution and evaporate. Then this could be a mixture of a solvent and a non-solvent. And if the solvent evaporates faster than the non-solvent, then that thing as it dries will go through a phase separation, so you can control the structure of it. Right. So that's the game they play. There's various ways to do that game. So you can put the thing into solution and then quench it into the non-solvent is always water. So NMP is like the normal solvent. Yeah, NMP is interesting. Like you spill it on, this is what I've done, spill it on your counter, the screwdriver handle goes in it, then the screwdriver handle is gone in like 10 minutes or something. So it's like super soluble for everything. Even cross-link stuff disappears in NMP, you know. It's pretty weird. Anyway, it's kind of toxic too, I think. They closed down Eero's lab for NMP, like he was using it for something. Apparently he was too loose with it or something, and he got into a lot of trouble. And then he made the argument that it was such a common thing and it wasn't that dangerous. They didn't buy that. So anyway, some of the solvent, yeah, the health and safety people said it was like super dangerous, and he was just using it all over the place. So anyway, he got into big trouble with that. Like they almost like killed him or something for it. I don't know.
Because Solvay just had like a pretty big innovation in switching their tuberosidone into NMP for safety reasons. So I wonder if like tuberosidone is more dangerous or something.
Must be. Yeah. Yeah, I bet it is. So anyway, who knows? But or they could have been overreacting too, but basically, I think that lab doesn't have a vent and it doesn't have a hood. So it's kind of like working with it without a hood. It's not maybe anything's a little bit dangerous. I mean, if you want to do this doctor blade thing, so you can just have a casting solution goes down and then cast it onto, so this thing becomes a rotating drum. And then somewhere here is a blade. Maybe one of these has a blade. So there's two things. You can do a doctor blade, or you can do a what do they call it? A web thing or something. So you just put down a film without the blade to make the thickness. So you control the thickness by the kind of how fast you feed it. I think that's a doctor blade right there. And then let's see, this is going this way though, huh? Oh, this is like a cloth, like a paper web that's going to go in. And then sometimes there's a paper web that goes, this is just on a belt making a solid one, right? Why are the directions going backwards? Dry film to take up, and then where does it come out? Casting solution. That's what it looks like. Yeah, but what are these arrows? Oh, this is the airflow. Sorry, that's the airflow to dry it, and that's the thing drying out. And then you just get the film from that, just like here, but with no. So you can have a substrate or not have a substrate, or you can do this like temperature phase separation. I mean, in a lab you do it in a press, but there's a machine here somewhere that shows it. Anyway, so there's a lot of these in here. So I just want to show machines, basically how these are made. This is a nucleation track membrane. So you're going to make ions and then blast the piece of plastic with it. basically, and it's like bullets that go through. So this is a pretty common method to make membranes. Like these are straight through holes that are like 10 micron in size. It's like burning a hole through a laser. And you just spray it with ions. So that's like a pretty popular method, but basically those are specialized membranes where you need a monodispersed pore size. Like they're all exactly the same size holes in it. So it's more expensive too, I think, than the others. And this is just like a polyolefin, like we saw, if you guys went out to Lion Dell, they have that film blowing operation, right? So you can just use that if you get, so the polymer comes out and crystallizes somewhere. It's called a frost line. It gets cloudy. And depending on where it crystallizes and where you draw it out, so it could crystallize over here, it could crystallize over here, depending on where that crystallization happens. So how fast it cools, you can get different structures. And one of the structures you can get with polypropylene is this holes, right, that are kind of uniform in size, 1 micron holes. So then you can make a big sheet that you can cover a house with, like that Tyvek stuff. I think was made of something like this. Yes, it's basically going to be moisture barrier. Yeah, it's just tearing as you process the thing. There's different ways to do this. P&G has, like if you look at the P&G diapers, like and the inside is like soft fabric, but it's not a non-woven. So that's made by a process like this too. So if you get the pores to be the size of your fingerprints, like the size of the ribs in your finger, it feels soft. So you can just extrude something that comes out feeling like fabric by using that same kind of process. So they've perfected that. But for the Tyvek, I think it's something like this, like you can just make a huge vapor barrier. Yeah, and then like lithium ion battery, you have to separate the anode and cathode. Right, see, this is a electrolyte in between this phosphoric something or other, right? Some kind of nasty thing that burns when air hits it. And then these membranes are in between the two to separate so they don't arc or whatever. My big thing is that it grows a dendrite across the electrodes. So you need something to prevent the dendrites from going across and burning out the battery as it charges and discharges. So these are one of the things that they use for that in a liquid electrolyte. You can also have like solid electrolyte, but that's kind of in development, I guess. But anyway, so this is just showing like just a process where I don't know what this is. This is just an extrusion of a film process. I think this is a non-solvent melt extruder to make polypropylene membranes by template leaching. So this is they're extruding something with like starch in it. Like you put starch in, it's water soluble. And if you have fairly uniform size starch, then you should wash it with water and the starch comes out. This is also like, if you don't do the wash step, that's biodegradable plastic. That's basically what they call, like when they say a biodegradable like dog bag thing. Mostly it's like some kind of polyethylene and they just put a bunch of starch in it. Like put the starch limit at 30%. And then when the starch washes out, the extraction step, then it just falls apart. Or you could control the starch level and then extract out and get pores. So these are like common processing things, right?
What does it end up being after the starch falls out?
Then you get a pore. What do you mean? When it falls apart, it's still polyethylene.
Oh.
It's just really small pieces of polyethylene.
So it just like increases.
Yeah, this is biodegradable. I mean, so it's still right. The good news is that polyethylene doesn't do it. It's wax, okay? So it's not going to do it. It's high molecular weight wax. So, like, do you worry about the candle? Like, it can burn,
Yeah.
And then the main thing is like some animal's going to get its head stuck in it, and then it's going to walk around with a beer ring thing on it, for the rest of its life or whatever. So, or that thing, so bad things can happen. But anyway, in the end, like if it's small enough, it's just fill, like it's like rocks. I mean, I don't know. Like, and then if it degrades, well, it'll be like ethane. I mean, I don't know. It's kind of like worrying too much about polyethylene is kind of a weird thing, when there's a lot of other things that are really dangerous that are around,
But like, what would even be the process? That you would go to a grocery store and get your stuff, and then you go home and like, I mean, obviously, most people would throw it away. But
Well, you throw it
people-
away and it gets wet. No, it gets wet when it's thrown away. So then the starch goes away when it gets wet. And it just becomes a little tiny micron size polyethylene, which is microplastics.
Yeah.
But again, like what actually do microplastics do to you? And there hasn't really been any study that says like they're bad for you. Like the Teflon thing, the fluorinated stuff, yeah, they kind of have some evidence. But wax, I don't know. Like, I don't think there's any study that says like wax is bad for you.
Yeah,
I mean,
it's not like it just came out last year, which I think people-
yeah, I mean, it's not ideal, but basically, there's a lot of things we should be worrying a lot about, that we ignore. Like tires are an interesting issue. Like, so your tire, like an eighth of the weight of your tire disappears as you use your tire, right? Yeah, and it's got sulfdiols, it's got all kinds of stuff in it. There's some stuff they know like kills fish and things. So that 1/8 of your tire, like where did it go? That's the question. So it's like out there, and it's also like, so you get basically nanoparticle or microparticle tire wear particles. They're all over the place in the environment. Some of them are airborne because they're small enough that they become an aerosol. Then those go up into the troposphere or something. So people have studied this with computer simulation. They find out like China's tire wear particles end up in California. The US wear particles from the East Coast end up in like Iceland and Europe. Yeah, because the small ones, which are the dangerous ones, because they're porting all the chemicals that go up and like fly over,
Yeah. So there has to be more than just like the wear on the tread, right? Like there has to be something like actually seeing out of the tire.
Yeah, the tire disappears, right? I mean, it wears out, so the stuff goes somewhere. Anyway, that's it turns out that's 50% of the microplastics in the environment.
Seriously.
Yeah, no one ever thinks about that. No one's saying like get rid of tires. Yeah, where are the people like ban the tires? It's like, so the fact is though, you can't have any modern technology without tires, but you can't make a car without a tire. Even an electric car has tires.
Right.
It's like a tire is like you can't negotiate it really. So that maybe you could deal with figuring out how to collect the particles or something.
Yeah.
So anyway, there's a lot of problems like that that are much more important than plastic bags.
Sure.
I mean, I think.
Yeah.
So
I think it's just because people see them, they're like, oh yeah, this plastic is bad. But like the
Yeah.
time that you're not really thinking about it.
I mean, there's also an issue of like, say like a glass, yeah, you can recycle it, but it weighs a lot. So you're burning fuel to move the glass to wherever. And the plastic doesn't weigh anything at all, like nothing, almost nothing. It's so thin, And the other thing is, it's like almost no material there. Like they can make bottles now that are so thin that like there's nothing there. So, I don't know. Anyway, it's kind of like at some point you got to say like do a whole system analysis, lifetime analysis, and say, is it really that bad to have a PET bottle? If you could make it a tenth of the thickness. So the technologies now for that are they can go a tenth of the thickness they have now. So they can make like 10 bottles for one. Yeah, a PET bottle, like a soda bottle. Because they can improve the barrier through processing. So I mean, I don't know. It's kind of like you wonder if you can do that, like, is it really worth worrying about that much? So I mean, it's a volume issue at the landfill, but you can kind of deal with that different. Anyway, it's possible to deal with it different ways, but PET isn't as good as, I mean, the long-term degradation of PET is like organic chemicals, like not ethylene or something, or ethane. So it's kind of like PET is a worse polymer, I guess, in polyethylene. But something like 80 or 90, 85, 82% of the waste is high density PE or polypropylene. So PET even doesn't make that much of a contribution. It's like 10%, 5%. So who knows? Anyway, so we're not getting too far on this stuff, but that's good enough. Oh, so the paper is though, so there's this thing, did you guys ever see nylon rope trick? I used to do this in the classroom, except I found out that this hexamethyldiamine is a tetragen, a carcinogen, and the other kind of gen. It's like, apparently it's not really legal to do that in class, but it's pretty simple. You put that into cyclohexane And then this sebaceous chloride goes into water. And then so you can have two solutions, like the water, the oil and the water. And at the interface, they go through this condensation reaction, make nylon. Right, so you can put a tweezers
And
in.
you stick something in.
Yeah, you put tweezers in, you can pull it out. You can make a strand from that. So this is exactly what they do for membrane. So the membrane in the paper is going to be this nylon membrane. They don't use that nylon. They use like a nylon like this. It's the same thing as an amide. So this thing would go into cyclohexane, and it's a carboxylic acid. So that's going to make water when it comes off. The other one's making hydrochloric. They're going to have Cl, HCl coming off. And this one's making H2O off. And then this makes this aromatic polyamide. Is stronger than nylon 6. So that's how they, yeah. So basically, various ways of doing the nylon rope trick. You soak your fabric like paper in the hexane solution. Then you dump it into a water solution with the chloride, and then the polymer forms at the surface. And then it phase separates when that happens, and you can form these weavy structures. Right, so you can have a porous substrate layer and then make your polyamide surface layer that's your selective layer. Then tuning that process however you want to do. Right. So it's basically a nylon rope trick, but with the aromatic polyamide, and then you can get super membranes doing that. It's like, so that's a whole category of membranes, like the cellulose acetate, cellulose nitrates, the basic original one for osmosis, reverse osmosis. And then this is like a higher tech one where you can have a graded, you can have this porous part, and then you can selectively just have a very thin selection layer that you form. Right. So that's like the so there's different categories, but that's one category. There's a bunch of different ways to do that process. So people are interested in these polyamide separation membranes. Anyway, so that's what the paper is on that I'll talk about Friday. Maybe we'll do a little bit more of this, but I actually have like 150 slides on membranes that I haven't exactly sorted through, right? But so there's a lot in this. So we'll see how far we can get through it. But anyway, why don't we quit there? It's past time, but so, right. Yeah. Internet fixed.